Chapter 5, Probability Distributions. A probability distribution is a list, and that's in parentheses because there may be an infinite number of things on that list, so it's not like your shopping list. But it's a list of all possible outcomes of an event or trial and their probabilities or likelihoods. So, how long does it take me to get to work in the morning? The probability distribution of that would be all the possible times from maybe 17 minutes to an hour and a half, and the possibility of each one of those being the actual time. Okay, so let's suppose we're going to look at student grades on a test. The sample space would be all students and their grades. Variable is their grade on the test. It's a random variable. In other words, it meets the criteria of the word random, which we theoretically already know. And in this case, it's a discrete random variable. And what we mean by discrete is simple. It's possible to get a 90 on your test or a 91, but it's not possible to get a 90.5. There are values that have no values between them. That's what discrete means. Values that have no values between them. So test scores or letter grades, A, B, C, or A plus, A minus, B plus. There's nothing between an A minus and a B plus. There's no B plus plus or A minus minus. That's discrete. Okay? So random variable, there's a pattern, but I can't just hear a student's name and know what their grade's going to be. There's a distribution, a spread to how their grades turn out. Okay, if I'm looking at how fast cars drive out on the freeway, the sample space is all the cars on the freeway, and the variable is their speed. In this case, it's a continuous random variable. Continuous means if I have one car that's going 70 and one car that's going 71, a car could be going 70.5. If I take the car that's going 70 and the car that's going 70.5, another car could be going 70.2. If I take the car that's going 70 and the car that's going 70.2, there could be a car going 70.1. If there's a car going 70 and a car going 70.1, there can be a car going 70.05. No matter what, there's always a speed in between the speed of any two other cars as long as those two cars are not going the same speed. So, discrete, we can have two numbers that have nothing in between them. Continuous, any two numbers always have some other number in between them. So discrete, continuous. Okay, so let's say we're actually in class and not sitting at home, and we want to figure out what the probability is of the gender of the next two students who walk through the door. Will it be two male students, two female students, a male followed by a female followed by a male, and so we have four possible outcomes. Four possible outcomes. And those four possible outcomes would be MM, MF, FM, or FF. And suppose we know that 60% of our students are female and 40% of our students are male. And again, assuming that everything's random, what's the probability that the next two students who walk in the door are male? Well, we can do some math here. So we're looking at two students and the number of females. So we'll make X, the letter X, represent the number of females. And I know I said males, but females doesn't really matter. So what's the probability of MM? Well, the probability of an M is 0.4. And we know how to do this now, right? Because we all aced our first exam and we aced chapter 3. 0.4 times 0.4 is 0.16. Probability of MF is 0.4, 0.6. We multiply those together, we get that. Okay? So the probability of no females walking in, X is 0. Probability of one female walking in would be the sum of those, which is 0.48, right? And then the probability of 2 females would be 0.36. And how do we know we did this right? This adds up to 1. Okay? So now we simplify this by making x be the primary value, and then we put x with its probability. So we have a 0, we have a 0, we have 1, and we have 2. And this is the probability distribution of the number of females. So we have x, and we have 0, 1, and 2 is the possibility, right? We're having 2 students walk in the door. 2 students. 2 students. And x is 0 females, 1 female, 2 females. Probability of x is 0.16, 0.48, 0.36. Again, has to add up to 1. This thingy right here is the probability distribution. Okay? We could draw a graph of that looks like this. What's the probability? 0, 1, or 2 females. That's a probability distribution. Okay? Pretty exciting, yes? So the expected value, which again we remember is another word for the mean, is the expected number of women to walk in the door, which would be the mean or average number of women. And that would be the mean equals the expected value is just the sum of x times p of x. So back here, we're going to take x times p of x. We're going to multiply all those out and add that up. And that's the average. And you're saying, pretty interesting. In the old days, before computers, we used to not exactly calculate averages. Statisticians would say there's 10,000 zeros and 20,000 ones and twos, and kind of estimate by going x times p of x, and they would come up with an estimate of the mean, or a guess of the mean, an approximation of the mean. So if we do this, we take 0 times 0.16, we take 1 times 0.48, we take 2 times 0.36, and we get 1.20. So in this case, if we look at 2 students walking in the door, on average, 1.2 of those 2 students would be female, and 0.8 of those 2 students would be male. Okay? All right. So there's some formal versions of these. There are specific probability distributions we want to look at. One of these is called the binomial distribution, and it's a discrete distribution. So discrete, yes? Discrete. We're looking at 3 different kinds of discrete distributions. And the first of those is the binomial. The binomial distribution applies when we have what's called a Bernoulli process. And if you don't know Bernoulli, there was this family of Bernoullis, and they invented all kinds of mathy things. So one of the things they invented is this Bernoulli process. In a Bernoulli process, we have an unknown number of trials, n. We're going to try something a certain number of times. It doesn't matter how many. But there can only be 2 possible outcomes, success and failure. So woman might be success, male might be failure. Or it might be playing on the roulette wheel and getting red or not. Or it might be rolling the dice and getting a 7 or not. It might be passing or failing the test. It could be anything that you can categorize as success and failure. Number 2, a Bernoulli process has to have a constant probability for the events. And number 3, they have to be independent events. When those 3 things are true, where we have 2 possible outcomes, n trials with 2 possible outcomes, constant probability and independent events, we have a Bernoulli process, and we can use the binomial distribution.
I don't think it means what you think it means.
All right, so the binomial, what do we get? We get these math problems, these probability problems that are difficult for us to solve just mathy-wise. So if you play only the number 12 on the roulette wheel and you play it 50 times, what's the chance that you'll win 3 times or win more than 3 times? Well, that's a potentially nasty math. And if we say, what's the chance you'll win 27 out of 50? That's It's ugly math. So the binomial distribution simplifies it for us. Okay? And lets us do this, and I'm not going to do the math for you. You're going to do the math in Excel if you were going to do it. In Excel, there's a pre-calculated thing called binom dist. Get rid of the eel. So there's a thing called binom dist in Excel. In Excel, there's a little button that looks like this. There's a little F with an X. That means functions, and one of those functions is binom dist. And if you go to binom dist, you fill out how many trials and what the probability is and how many successes you want. So 3, for example, you might put in 3 of 50, and the probability of a 12 is 1 in 38. So you would figure out your probability, 1 in 38. And you would put that in Excel, you'd put 50 in Excel, and you'd put 3. And it would solve the problem for you. Okay? So we use binomial to solve these specific kinds of problems. When we take a sample of something, and we'll talk about this more when we get there, we sample 2 ways. One is called with replacement, and the other is called without replacement. Pretty complex. So you have the names of everybody in class in a hat, and you're going to pull out 2 names of somebody to win a prize. Sampling with replacement means you pull a name out of the hat, you read that name, and then you throw the name back in the hat. So you have 2 prizes that could be won by people in class. The same person could win them both. Sampling without replacement, you take that name out and you throw it away. So now you have the second name you're going to pull out cannot possibly be the first name. So sampling with replacement is like a roulette wheel. When a number comes up on the roulette wheel, we don't take that number off, we leave it on the wheel. So every time you roll the wheel, the number 10 is there. That's sampling with replacement, and it tends to give you independent events. Sampling without replacement is playing cards. When you take the deck of cards and you play an ace out of the deck, there's 1 fewer ace left in the deck, and that changes the probability. And once you've played all 4 aces, you've really changed the probability of getting an ace. So sampling without replacement creates non-independent events, creates events where the probability is going to change. So binomial is sampling with replacement. We can do the same kind of problem if we're sampling without replacement. And an example of this would be a Keno or a lottery. In a Keno game, there's 80 numbers in a big bucket, and they pull out 20 of the 80 numbers. The first number has a chance of 1 in 80 being drawn. Once we pull that number out of the thing, there's only 79 numbers left, and the next number has a 1 in 79 chance of being drawn. And the third number has a 1 in 78 chance of being drawn. So the probabilities keep changing. If we try to calculate those probabilities, it becomes very complex. The same thing if you're looking at the California lottery or the Mega Bucks or the Powerball. There's a group where you have to pick 5 numbers. Well, there's, say, 70 numbers on that list. The first number has a 1 in 70 chance of being chosen. Your second number has a 1 in 69 chance of being chosen. It makes the computation a lot more complex. So when we calculate without replacement, doing Keno or a lottery, we would use something called the hypergeometric distribution. And again, if we went into Excel under f of x, there's a hypergeom dist, and it lets you put the numbers in. What's the probability? How many are we doing? So if it's the California lottery, you'd say, there's 70 numbers, and we're going to pick 5 of the 70. All right? Or if a Keno game, there's 80 numbers, and we're going to pick 20. Now, Keno's even more complex because, well, in both cases it's more complex because you don't have to get all 5 to win here. You don't have to get all 20 to win here. You can bet 8. So you bet 8 numbers. You want your 8 numbers to come up in those 20, which are coming from the 80. Again, very complex math. Think of the tree you'd have to draw with, 80 possibilities, and then. But we can put these numbers, these points, plus the probability of each number being chosen there into the hypergeometric, and poof, out will come the answer. And we don't have to do a lot of math and a lot of calculating. Okay? And then the third, and again, remember that this is also discrete, right? You can't go play the lottery and tell it you want the Powerball to be 15.5. You're either going to have to pick 15 or 16. There is no 15.5 on the list. The third distribution that you might have, and again, it's in Excel. If you go to FX and you go look for Poisson, it's there. Okay? Poisson distribution is a distribution of rare events. It was actually invented by a guy who was a doctor in Napoleon's army who wanted to figure out the pattern of how often soldiers got kicked in the head by their horses. And it doesn't happen very often, but occasionally a horse gets mad at their rider and kicks them in the head after they get off. And this doctor figured out that there's a pattern. So it's infrequent events. What we say is infrequent outcomes that occur along a continuum. A continuum could be a period of time, like the horse thing, every day over the course of a month. Or it might be, for example, standing in line. It might be an assembly line where products are rolling off the assembly line. A continuum means some kind of continuous thing, time, a line, an assembly line. Okay? So where we use Poisson in the real world is lines at a bank. We could use Poisson, for example, you have a line, a bank, or maybe the front desk of a hotel. And what you want to do is figure out, based on how many people show up per hour, minute, day, what's the chance that you're going to have more than 5 people in line? If you're a grocery store and you put extra cashiers on, if you get 3 people in line, what's the chance that happens? You can figure out what goes on with the line, or you can figure out if you normally have, in every 1,000 you make light bulbs, and every 1,000 light bulbs there's one defective one. What's the chance that in 1,000 light bulbs you're going to have 4 defective ones? Okay? So Poisson is about lines, assembly lines, and things that happen infrequently along a long continuum of time. Okay? So those are 3 discrete distributions that we see all the time that, again, you don't really have to know how to calculate. Excel would calculate them for you, but you have to know why you might hear them. So you would hear binomial because we're doing some kind of sampling with replacement, like a roulette wheel or the big wheel thing that spins around at a casino, and we're trying to figure out the chance of some odd, what's the chance that if I spin this 1,000 times, I'm going to get exactly 642 black? We can figure that out with binomial without having to do a lot of crazy mathematics. Hypergeometric, Keno, lottery, those kind of games, we can figure out how likely we are to get certain combinations there. And then Poisson would be lines, whether it's a production line, standing in line. What's the chance that line gets longer than we want, or there's more defects in that line than we think, or too many of our soldiers are getting kicked in the head by a horse.